Hey, what's going on, guys? Komiki here. In this video, I'd like to share some tips and tricks on debugging your code written in x86 assembly that I'm using, and probably this would be useful at least to someone. So things that are incredibly easy to do in C programming language, for instance, or in whatever high-level programming language, like as opposed to assembly, I mean. You can simply just use print or printf or whatever function and then just print the variables. However, in assembly, it's not that trivial. So I've decided to, well, eventually I've ended up with my tiny little, well, I don't really want to call it a framework, but it's something similar to a framework that allows me to print the variables. So I can print a byte and single byte. So if I need to inspect the variable, I can just print a byte, and also I can print a word for kind of like 16-bit variables, right? So how does that work? Yeah, so I'm working on 6502 processor simulator. It's going to be a bootable, well, you probably can think of it like as if this was an operating system, I believe. So it's going to be booting into some sort of an environment, like some sort of a simulated environment where the processor would be able to receive the commands in the form of 6502 machine codes, and then reading those machine codes from the simulated memory, and then trying to execute whatever those opcodes and the values are going to be telling it to do. So it needs to be very precise, hence the need of this debugging environment, let's say. So the way how I organize the files here, so well bootloader is self-explanatory, just boots all we need. But here is the deal. So I previously, when I was working on the previous project that was an operating system to run boot sector games and apps, I had all the debugging procedures being duplicated in every next file I was using. But here I decided to make a single file with global procedures, and here is the file. So the global procedures that can be referenced from whatever segment using the var calls, and every global procedure makes this return var. So it's not obvious to have this code in every single file now. So that's one of the core things behind the design solution. Also, these global procedures do rely on some local procedures, so they just return locally and only being called from this global procedures. And now, in order to reference these procedures, so these procedures are loaded at address 7E00, and in order to reference them globally, I just need to calculate the proper offset for every function. And once I've done that, I actually have these offsets being defined here. And from now on, I can call the procedure from a different segment. Well, it's not exactly from a different segment, but from the var call perspective, this might be treated as the function from a different segment. So I call this function from this global procedure scope like this. So this is the 16-bit real mode specific addressing modes, right? And so yeah, I have the kind of the address of where the procedures leave, this one, and then the local offset for relative to this global place where the procedures leave, basically. So that's kind of pretty much all about it, right? And now I just want to demonstrate how these procedures work, and I will end up writing a little routine that I actually need to write anyway. So here in 6502 processor, we have only 3 general purpose registers. This it's called register P, but literally it's just the processor flags. Just 7 bits for, like 8 bits for processor flags. Well, actually 7 bits, one is reserved. Then the stack pointer, which is byte, and the program counter, which is a word. So I need, so here I have the string to print all the registers, followed by the new line and carriage return. Have some the new line carriage, the new line character if needed as well, because print byte and print word. Well, I'm not sure about the print word. Actually, does the print word print address? Probably. Hold on a sec. Yeah, probably doesn't make. Yeah, it doesn't make a new line after. All right, so let's go for a quick demonstration, and we'll start with what? Well, let's kickstart with the print string, which is the most trivial one and which we will need anyway. So bear in mind the fact that I've already initialized the data segment to where the CS is pointing to, which is the code segment, and so instruction pointer points here when it jumps. I initialize this value to AX and then transfer to DS, right? So which means that DSSI would be pointing to the relative offset starting from 0 and then to whatever offset we have to the variable that we need. So here in this case I can simply say move SI and print registers, which is going to be just printing this line. And now I can say call procedures and print string. And if I did everything properly, it now should print all the registers, which it does, right? So don't get confused by the video mode. So this is 40 by 25 characters textual mode with a custom attribute for a foreground color for a text, because I'm inspired by the Apple I computer, and I'm trying to make it look and feel something like as it was an Apple I computer. Hence this debugging information is kind of like done like that. If needed, I will now just alter the spaces as well. But anyway, and now first let me just show you this in separate. So this prints the new line already, but now let's say, so here is the interface for print. So the next thing I'm going to be doing, okay, I just want to show print memory as well. So yeah, that's just another very useful routine, which is worth of showing. So I just get rid of this temporarily, and let's say I say move. In order to make this, I need to reset the data segment. So I need to say XOR AX, move to DS. I want to move AX, so DX is now equal to 0, and now SI is going to be equal to, let's say, the boot sector, and we'll now see the first 8 bytes being available at the boot sector, and literally those here, right? Like obviously not the assembly code, but the corresponding machine code after it has been assembled and loaded. So if I just say call procedures and how do I call this? Print memory. Okay, print memory, and save and run. All right, let's have a look. Yeah, and we got 1, 2, 3, 4, 5, 6, 7, 8, first 8 bits. Well, just to give you an idea, these are exactly, well, by the way, it also prints the address of where a size points into. Just to give you an idea that these are not just the random numbers, but actually the numbers we have. I can just verify them using the hex dump. So if I just go to the virtual x86 emulator and load my image from here and start emulation, it would now print the same stuff, but I would then download. By the time it's loading, I can go. Oh my god, it's so slow for some reason. Yeah, I can go to my downloads folder to clean up the files from the previous attempt. Doing this. Okay. I know it's so. Why it's so laggy? Yeah. it finally works. Yeah, I don't know, my computer is going crazy for some reason. Yeah, that's the reason why it's just slow, but it doesn't matter really. So I just go to downloads. Yeah, okay, I don't have anything here. So now I just can download the memory dump, and once it gets downloaded, yeah, here it is. Here we go. We can inspect this exact address and to verify the numbers, just to make sure that the debugging routine is actually working properly. Okay, so yeah, here we go. All right. Okay. Yeah. Sorry guys, just close the minimize the browser. I don't know, for some reason why it's so laggy. Why is that so laggy? Maybe just close this one at least. Yeah. Okay, much better. So I just want to open the terminal here and inspect the memory, and I'm looking for 7C00, which is the boot sector, and here are the bytes. So we need to verify the first 8 bytes, so 8C, C8, 8C, C8, 8ED8, 8ED8, 8ED0, 8ED0, BD00, which is exactly the case, so which means that our routine is working properly. So now you see, like, instead of spending time on getting this hex dump, I can just inspect whatever happens in my environment without being bothered by generating this hex dump. So I don't need some extra debugging stuff or something. So I can literally point SI to whatever memory location, and then I can just simply print the memory there. Not obviously for one line, so I can make this in a loop. And in this case, this is going to be done like, well, just to give you an idea. So let's say loop, and here jump to loop, and let's say compare SI with, let's say, until it doesn't get to 7E00, and let's say jump greater equals jump greater or equals to the end, for instance, and here we can say the end. And now I can print already a chunk of memory. By the way, this nice cute effect of printing like slowly is a side effect of what I've achieved because of setting the color attribute. So as you can see, yeah, and here we end up with a bias signature, by the way, which makes like absolutely sure that this is the exact location, so it ends up with a bias signature. So we just printed the entire boot sector. Well, obviously it scrolls up, which is not really that great. Like you can see what is there, but I'm not forced to print the entire 512 bytes. I can just type the number of lines I want. So 1 line, 2, 3, whatever. So 8 bytes per line, no matter how. So I can type. I can print whatever number of lines, and I'm not sure why Camo is printing the zeros. Not the best, greatest ever way, but on the real hardware it actually looks much better. Okay, so I hope it's clear in regards to the print memory, which is, yeah, again, like one of the core procedures, because using this procedure I would also be capable of inspecting the simulated memory, or well, simulated that the processor that I'm implementing is going to be setting value to or fetching values from. So it's very useful routine to keep track of whatever part of RAM in 16-bit RAIL mode x86 environment. So it's very useful and it doesn't really take that much of code to come up with. This project is not yet being published, but if you're interested, please let me know, and I can send you this code. So it is going to be published once I come up with something decent. But for now, I'm just not publishing this because it's a pretty early stage. But maybe by the time when you would be watching this video, the code would already be published. So we'll see. All right, so this was the print memory routine. And now let's have a look at print byte and print word. So let's have a look what arguments does it take. So print byte, AL holds the argument to print, so we need to initialize AL to whatever value we want to print. The byte we want to print, we want to put that byte into AL and then call this print byte. So let's say I can say move to AL 0x, let's say 23 hexadecimal, and then I can say call procedures and print byte, and again, like here, the local offset starting from where procedures are available in the memory, making this var call, then return from there, right? And here I can see, so this 23, we just printed that quite pretty nicely. Okay, so now let's say I want to put some value, let's say df, for instance, to a real variable, and in this case I can simply say to AL I want to move the byte at the value of the byte at the register A, and it should print df, and it does print df. So we have everything literally in order to print the routine that would be printing the state of all the registers in one run. So let's actually go and do this. So first, I want to print the registers, and then, so what bytes, I just put this several times. It's okay for debugging function, it's just okay. So register A, register Y, well, I didn't show how to print the word, but it gets self-explanatory now. Register X, register Y, register P, which just the processor flag. So in order to decode this value, it should be observed as a binary, but for debugging it's literally enough to see the like hexadecimal value and then this hexadecimal value of 20, right? It turns simply to 00100000, and this is how we know which flags has been set, which not, because we have the mapping right over in here, so we just can map the flags like this, and that's pretty much all about it, right? So here we got our mapping for the flags, so it's also quite pretty useful, right? Okay, so what else? P, so processor flags, then the stack pointer. So here I want to print the stack pointer, and at very last, so this time, if I want to print the word, I need to use the AX register, right? So I can simply say move to AX and program counter. So this is the only 16-bit register in 6502 processor, which is cool. So you can reference up to 64 kilobytes of RAM potentially, even though the computer might not obviously have that amount of memory, like Apple One only had 8 kilobytes of memory. So program counter, so yeah, I want the word, add the program counter, right? And call procedures print word. So let's have a look what kind of output we will get in return. And yeah, this is pretty cool. I just only want to fix the layout. So yeah, here I just want to just make it like this apparently. Yeah, now it's much better. So processor flags, stack pointer, and program counter, and yeah, and then I can simply print the new line to end up with this. So I can simply say move to SI, the new line, and call procedures print string. All right, and here we go. I got a new line, so whatever next to be printed, it would be it would start from the new line. Okay, guys. So yeah, I think this is it from my side. Yeah, let me just quickly demonstrate this. So just let's take some custom values. Yeah, by the way, hold on a second. Did register a? Yeah, df was okay. Yeah. So let's say like, yeah, df here we put some like whatever numbers, and here let's say like 1 2 3 4 hexadecimal, right? And if we now verify the values, so these are exactly the values that we have. So a df, x hexadecimal 12, y af, processor flags hexadecimal 20, stack pointer fe, program counter 1 2 3 4, which is exactly the case. So I think this is good enough for debugging. Well, at least I'm pretty happy with this result. So I have no idea whether it was useful for you guys or not, but if you're interested in using this sort of a thing, please just let me know in the commentaries, and I'll provide the source code so you would be able to make use of it as well. And if you're interested to know how exactly the source code works, well, just a very brief overview apparently. So the hex, the core routine is to print the hex number. What it does literally, it just distinguishes between the digits and the letters, digits from 0 to 9 and the letters from A to F, including F, and then it either converts digit to ASCII or a letter to ASCII. So by simply adding the ASCII value of 0 or of big A minus 10, because that's the exact value of what A means, what A is equal to in hexadecimal, right? And then it just printing the character to screen. That's pretty much all about it. Well, call set attribute just makes the character green, nothing special. And then what we need to do here is we just need to, so the cool thing about hexadecimal, so every digit or letter always represents a nibble, which is 4 bytes. So if we want to print the byte, we just masking the byte like this. So just the left, like the most significant nibble is being masked, and then we shift to the right, and then we just call this print hex. So so print hex assumes that the least significant nibble is the character they want to print, and then for the other character, it just masks the least significant one, and the rest gets reset, right? And then we print the hex again. When it comes to printing the word, I'm reusing the routine to print the address that was used in the print memory. So print memory calls print address. So initially it assumes that the address is stored in SI. So there's a little work to do. So just moving the value of AX to SI to make AX as the argument, which is natural, right? And then I'm doing pretty same thing, but masking the word. So see, like F here, then shifts here, here. I'm shifting the needed amount of bytes when necessary, and then just calling this print hex. And that's pretty much all about it. And that's how we can inspect the values of hexadecimal numbers or whatever variables. And well, for me personally, what I was doing kind of when I just started assembly back in the day, I was thinking like trying to print the decimal values like in C programming language, but it's really much more complicated thing to achieve if you want to print this decimal numbers. But with hexadecimals, it's really trivial. So just a few simple routines allowing you to have this fantastic output, so you can keep track of whatever variable you're interested in. Well, okay guys, this is it from my side. Thanks for watching. Until the next time, and take care.